Hi everyone, so this is the first video on aqueous solutions and aqueous reactions, and in this video I really just want to talk about a couple of important concepts that you have to know. There's not a lot of calculations here, it's really just kind of conceptual part of aqueous solutions, which is first what makes water such an important solvent and how does it dissolve a solute, and secondly, how do we differentiate among the different types of solutions that we have when the solute is dissolved in water? So the first thing we want to talk about is just what is the molecular basis of hydration. Now, hydration is this process when water dissolves a solute. That's what we call hydration. So the idea is what makes water such a good solvent? Well, first off, you have to understand that when water dissolves a solute, what it does is basically the water molecule makes electrostatic interaction, and remember what electrostatic interactions are. They are interactions that are made, by charged particles, so things that have positives and negatives on them. So the positive part would interact with the negative part, and then the negative part would interact with the positive part. That's what we refer to as electrostatic interactions. We talked about this in chapter 2 when we talked about the discoveries of the fundamental particles. Now, what water does is that it makes electrostatic interactions with a large number of solute molecules. So that's why water is often called a universal solvent, because it seems to have the ability to dissolve pretty much everything that you throw at it. So if you mix salt, table salt, for example, in water, it will dissolve. You take sugar, which is a completely different type of compound, it would also dissolve in water, and you can take other stuff as well, gases, liquids, they will all be mixing very well with water. So the idea is then, why is water so good at dissolving all kinds of solute? So the question that we're going to answer in the next slide is first preceded by the structure of water. So water looks like this. It has an oxygen atom, which is the red one, and it has two hydrogen atoms, which are the white ones. And we're going to talk about why this particular structure is so good at making electrostatic interaction with other solid molecules. So the reason why water is such a good solvent is given here. There's two reasons. One is that water, it turns out, is what we call a polar molecule, and it's a fairly polar one at that. In other words, it's we'll talk about what that means in a second. But once we know that water is a polar molecule, that helps explain why it could make these strong electrostatic interaction, which is, remember, the positive-negative type of interactions. So let me show you here the structure of water. So as I mentioned earlier, this is the oxygen atom of water, and these two are the hydrogen atoms. As it turns out, and you really won't learn this till a little bit later in the semester at the end when we talk about electronegativity, oxygen is an atom that turns out to tend to pull electrons to itself when it's involved in a covalent bond with other atoms. And specifically with hydrogen, a lot of the electrons are pulled towards the oxygen atom. As a result of having a fairly rich distribution of electron around the oxygen, in other words, it has more electrons here compared to the hydrogen atoms, the oxygen atom in water is what we call partial negative, because it has more electrons in comparison to the hydrogen. So we give it the symbol. This is a delta symbol, it's a Greek letter, and partial negative, meaning that it's more negative in comparison to the hydrogen atom. On the other hand, you can think of the hydrogen atom, because most of the electrons are pulled towards the oxygen, to be more positive, relatively speaking, in comparison to the oxygen atom. So then we give it a symbol delta positive for both of this hydrogen atom. Now, as the way we represent this then is as follows. We can think of water basically as having two poles. It has if you represent this using something like a magnet, for example, you can think of this part as the negative end of water and this part as the positive end of water. And so this is what we call a dipole, and any molecule that displays this type of property is called a polar molecule. So that's what it means to be a polar molecule. And the stronger these partial charges are, the partial negative and the partial positive, the more polar that molecule becomes. And as I mentioned earlier, water is fairly polar, meaning that the sizes of these negative and positive charges on water is actually pretty large, relatively speaking. Okay? And what that allows water to do is that it allows water to make interactions with other molecules that also have positive and negative charges. Okay? So if I have another molecule here, and let me draw this at another page. Okay, so you can imagine earlier the water that I drew has a partial positive, partial negative charge. Now let's say I have another molecule here, and I'm going to represent this using, let's say, an ellipse of some sort. And then this molecule has a negative and positive charge as well. Now of course, once you see this, the positive and negative charge here can then make interaction, and that's what we call electrostatic interaction. So here, your rectangle here is your water molecule. Here's molecule X that also happens to be polar. It has a positive, negative charges on it. Then water can surround this particular molecule. So another water molecule might come along here, and then the positive end aligns right there, and negative end right here, and then it makes interaction with this particle. Okay, so if you have a bunch of these water molecules surrounding the polar molecule here, what it happens then is that the molecule then is basically dissolved in water. That's what happens when a solid dissolves in water, is that the solid particle, each one of them is basically pulled apart by a bunch of water molecules. I'm going to show you an animation in a second of what this looks like for table salt. Okay. Now similarly, if you have something like an ion, like a positive ion for example, okay, a cation, water can do the same thing. If I have a bunch of these water molecules around the positive cation, okay, basically what happens is that you have the negative end of water making electrostatic attraction, attracted to this cation, and then the positive end here is on the outside. Okay, but that's what water does to anything that's charged. Okay. So if you look back at this slide, the one where I start by mentioning how polar water is, a fairly polar molecule, as I just explained, any kind of compounds, any kind of solutes that has some kind of charges on them can make these strong interactions with water, and as a result they will be dissolved in water. What are these compounds? Well, ionic compounds is definitely one of them, because ionic compounds, they are formed by ions, which are charged particles, right? Cations and anions are both charged. So both the cation and the anion can make interactions with water, and I'll show you again an animation of how this looks like. And polar covalent molecules can do the same thing, because polar covalent molecules basically are molecules that look like water. They also have positive and negative ends in one molecule, and then they would just reorient themselves in such a way that the positive end of those molecules would make interaction with the oxygen in water, and the negative end of those molecules would make interaction with the hydrogen end of water. Okay? That's just polarity. Water can dissolve because it's polar, thereby it can make all these strong electrostatic interactions. But the second thing that's really important that differentiates water from a lot of other polar molecules is water is fairly small. Okay? Now, the fact that water is small means that it can, as a molecule, fit into a lot of the different spaces that larger molecules cannot, just by volume consideration. If I have something small, then I can put that molecule into spaces, smaller spaces, that other larger molecules can't occupy. Okay? And the fact that we can have water into those spaces allows water to hydrate various types of polar parts of a molecule. Okay, and that's why water is such a good solvent, such an effective solvent. So here I want to briefly show you an animation which would kind of end this video, this first video on how water acts as a solvent. So the question that I'm asking here is, how does water dissolve table salt, which is the sodium chloride? So if you take a beaker of water and you put some table salt in it, you can do this experiment at home. You'll see that the solution is a little cloudy because at the beginning the table salt is still all there and they're not dissolved. But if you take a spoon and you start mixing, of course at some point the table salt is all dissolved in water and you no longer see any particles. In other words, this is your homogeneous solution of sodium chloride. Our question here is, what does this thing look like in atomic scale? So this is a little YouTube video which actually explained the dissociation of table salt in the presence of water quite well, and how salt is dissolved in water. So I'm just going to let it play, and then at the end of it point out a couple of important concepts there, and then we'll end the video.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions.
So I want to point out here that you can see in the animation that the oxygen is now surrounding the sodium ion, and sodium, remember, of course, is positively charged. The oxygen in water is partial negative, and that's why a bunch of them surround the sodium and start to pull it apart from the solid itself. So this is the solid table salt that you see, but once they're taken apart, then eventually that solid all breaks down and disappear and dissolves, and that's what we call dissolving.
The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Okay, so that was the first part of the video, and this is the end of it. In the second video, I will discuss a little bit more about how water then dissolves covalent compound, as well as how we differentiate among the different types of solutions.